It's my great pleasure to introduce Tuan Tran. So Tuan was the first grad student that I admitted, the first application that I looked at in anger when I joined the faculty at UC Santa Cruz in the 2014-2015 area. And man, has he had a journey. And part of his journey was as he went in search of his interests, he departed from my expertise. And like a smart PhD student, he went in search of additional mentorship. I saw our chancellor at a recent faculty visit day gave this speech, and it was like a chancellor speech full of glittering generalities. But one of the things she said was, you can never have, there's no upper limit to how many mentors you can have in life. And I just really strongly agree with this. Like, winning is like maximizing your mentors and going in search of the people who will help you do the work you got to do. And this was work that had to happen. I'm just so delighted. So Tuan will be talking about detecting and mitigating faults in BFT systems.
All right. Thank you for that awesome introduction, Peter. Thank you, everyone, for coming to my defense. I'm really happy to see everyone here. My name is Tuan Tran. Today, I will be presenting the work that I've done over my PhD, the topic of which is detecting and mitigating faults in Byzantine fault-tolerant systems. Today, I'm joined by my awesome committee members, my advisors, Owen Arden, Peter Alvaro, and also Alison Bassani, who is an associate professor at the University of Lisbon. All right, so to sum up my PhD in one slide, it is about enhancing fault detection in Byzantine fault-tolerant systems to make these systems more robust. Right? Byzantine fault-tolerant state machine replication is an approach to building fault-tolerant services. And in these systems, client sends requests, and a set of replicas will run consensus to reach agreement on an ordering for these requests before executing them. As long as a majority of the replicas are correct, good things will happen, requests will get processed in time, and we can ignore the bad things, ignore the faulty replicas. Right? And fault detection mechanisms exist in these systems, but they're not utilized to their full potential. So can we leverage fault detection to make these systems more robust? And to answer this question, I explore two classes of BFT systems. The first is the permission BFT systems, or the classical BFT system. These systems prioritizes strong consistency in exchange for a weak availability guarantee. So for these systems, I will look into how fault detection can be used to strengthen the availability guarantee. The second class of BFT systems I'll look into are permissionless BFT systems, or you might otherwise know as the more popular buzzword, blockchains. These systems prioritize availability in exchange for a weaker consistency guarantee. So for these systems, I will look into some of the ways in which inconsistencies can happen and how we can use fault detection to prevent these inconsistencies from happening. So why are we even talking about BFT, right? So BFT used to be primarily theoretical research. But that was up until the year 2016, 2017, when blockchains became really popular. And there was this realization that blockchains have made BFT practical at scale. Right? It's being used by millions of users worldwide. It's seeing investments from government, academia, industry. And so this, in turn, reignited research into BFT, with researchers looking for ways to adapt classical BFT techniques into blockchains and vice versa. So that's why, oh, sorry, go ahead.
I didn't mean to interrupt you, but what's the source for this?
Oh, this was from the UCSC database, one of the UCSC databases.
Like a library database?
Yeah.
And just based on like keyword
Keyword,
DLT kind of
keyword in conference publications.
thing? Gotcha.
So
I'm so sorry. May I ask which room you're in? I want to come actually.
Oh,
Oh, 553 in E2.
What? Say it again, please.
553.
two floors up. Yeah, 2 floors up. Season. So, I ask just because I'm a little surprised not to see more of like a bimodality, because like there really was all these like BFT protocols, and then around 2013 they really did die out, and I'm surprised it's not more of a.
But yeah, but that's what the blues are, right?
The blues are the permission BFT.
I agree. I kind of expected it to be like bimodal. Like there was all this excitement, and then it went really down, and then there was all this excitement again. But maybe I just had my magnitudes off, to be honest.
Mm-hmm.
Yeah, so there was some excitement, and then around 2017, 2018, like the excitement really jumped up.
Yeah, for sure. Yeah.
Yeah, so I mean, that's why recently this graph shows that there's a correlation in the increase in the number of blockchain and permission BFT publications, right? So yeah, that's pretty cool. For the first part of my talk, I will discuss fault detection in permission BFT systems. And for the first project I'll present, it's called Unstick Yourself, Recoverable Byzantine Fault Tolerant Services. This work was presented at ICBC of last year. Okay, so let's get a little bit into permission BFT replication. These systems consider a set of n replicas, f of which can be faulty. And there are two protocols that make these systems work. The first is the Byzantine commit protocol. It's a three-phase leader-based protocol that gets executed by the replicas once they receive requests from the clients.
Sorry.
And the three phases are typically the pre-prepare, prepare, and commit phase, with replicas in the prepare and commit phases waiting for a quorum of n-f messages before deciding that agreement has been reached and it's safe to move on. The second protocol in these permission BFT systems is a view change protocol. And it's used to replace a leader when good things don't happen. Right? A replica can choose to elect a new leader by sending a view change message. And the new leader gets elected once they have received a quorum of n-f of these view change messages. Okay, cool. So remember that these permission BFT systems prioritizes strong consistency in exchange for weak availability guarantee. So one of the major problems that these systems face is guaranteeing availability in prolonged deployments where faults can accumulate. And we can break that problem down into three parts. The first part is that these systems are inherently masking quorum systems. Recall that earlier, as long as we have enough correct replicas to make good things happen, we can ignore the bad things, ignore the faulty replicas, right? So let's take a look at an example of that. Suppose during consensus, one of the replicas, R2, here, decides to deviate from the protocol and sends everybody garbage. Right? But even without this replica, the remaining replicas are sufficient to reach agreement and move on from the prepare phase to the commit phase and subsequently finish. So although the correct replicas suspect that R2 is faulty because it was sending them garbage, they just kind of ignore it, right? They leave it alone, and to the client, the system seems like nothing is wrong. So we essentially mask the faulty replicas. The second part of this problem is that crashes are inevitable. It's impossible to guarantee 100% uptime for machines. Right? So an adversary does not even need to be all powerful as described in literature, right? It doesn't need to control replicas. It doesn't need to control message delivery over the network. It just needs to wait for the right time to deviate from the protocol. Let's take a look at an example of that. So suppose we have a system of 4 replicas and one of them crashed. During normal operation, replicas periodically send heartbeat messages to one another just to check if they're still up. And of course, when they send a heartbeat message to R3, it cannot respond. So the replicas suspect that their R3 is faulty. And this includes R2. But instead of just ignoring, R2 decides, well, now is probably the best time for me to deviate from the protocol and start misbehaving. So now there's only 2 replicas remaining. Of course, that's not sufficient to reach agreement. And the system is in a sticky situation. And finally, the last part of this problem is that to account for those situations, it would be too expensive, right? Our fault threshold F accounts for both Byzantine and crash faults. So for each additional type of these faults that we expect, we need to provision 3 additional replicas. Right? And of course, the more replicas that we provision, the more messages are exchanged during consensus, and the more it impacts our performance. All right, so I hope that I've convinced you that the problem of accumulating faults is pretty bad in BFT systems. In this work, we propose a protocol that will help deal with this problem of accumulating faults using fault detection. The idea is that don't just mask the faults, right? Detect them and replace them before they can accumulate over time and eventually surpass that fault threshold that we have. Recall that our parameter n, our parameter f accounts for both Byzantine and crash faults. So our typical parameter n would look something like 3fb plus 3fc plus 1. It turns out that we can overcome the same number of faults using a smaller deployment, a smaller number of replicas. Okay. We talk about overcoming the problem of accumulating faults using fault detection. But how is that done in BFT systems? Well, fault detection in BFT is actually a well-studied topic, with many BFT protocols in the past presenting various ways of detecting faulty replicas. Right? For example, as we've seen, leader not sending proposed messages will cause it to be replaced through a view change. In a protocol like aardvark, leader not meeting some sort of throughput requirement will also cause it to be replaced. And in a protocol like XFT, a replica not participating in the view change will get suspected. Right? So, but all of these fault detection mechanisms that are presented in these protocols ultimately leave the detected replica to remain as part of the active replica set, where they will accumulate over time. So we're not proposing any novel fault detection techniques here. We're not reinventing the wheel. We're just showing that the wheels can in fact be put on a car for you to drive. Right? So all of these fault detection techniques can not only be used to detect faults, but replace these faulty replicas. All right, so we talk about replacing replicas, but how is that done? So there's actually a third subprotocol in these systems that's less often talked about. It's called reconfiguration. And I'll note that although it's talked about in previous systems, only 2 systems actually come with a fully implemented reconfiguration protocol. One of which is BFT Smart. It's built by Allison. These reconfiguration protocols describe the existence of a configuration manager. And this configuration manager will issue reconfiguration requests And then replicas will reach agreement on this new configuration before replying to the configuration manager. I'll call CM now because it's a long word to say. And the CM will, once it receives enough replies, it will introduce the new replica to the active replica set. I'll also note that reconfiguration is only possible if there are enough replicas left to commit to the new configuration. So if there aren't, then we're also out of luck. All right, so the CM is instrumental to making reconfiguration work. But there's two assumptions that's made about the CM, though. The first is that it is trusted. But I mean, so what? Everybody's doing it, not just the BFT folks. We have crash fault tolerant protocols like Paxos, RAF, Zookeeper. Every one of these protocols make the assumption that there's a trusted configuration manager. Right, so we'll get back to this problem later. For now, we'll do what the cool kids are doing. We'll assume that there's a configuration manager and that it's trusted. All right, the second assumption made about the CM, and perhaps the more critical assumption, is that it knows which replicas are misbehaving, which is not always the case. The CM is not part of the active replica set. It doesn't see the communication that happens during normal operation. So a replica could be sending garbage to everybody else. And the only method that the CM has to infer how the replica is behaving is through some sort of heartbeat mechanism. And although this is a fine approach for crash fault tolerant systems, we see here it wouldn't work so well in a BFT system because the faulty replica can lie. Right?
Well, is this how the two that are implemented work? Or
I'm sorry?
is this the way that the two implemented configuration managers you mentioned work?
In BFT Smart, there's actually it's just a one shot where we should know beforehand which replica is faulty.
Yeah.
So there's no monitoring.
And what's the other one?
The other one's CCF. CCF, underneath, they use PBFT. And I haven't looked into their reconfiguration mechanism in detail, but from a quick look, there's no monitoring between the.
It's also just
Yeah, it's just a one shot where you need to know who's faulty to replace.
Yeah.
Right.
Yeah.
But this side, I'm hoping to convince you that it's not possible in a lot of cases. Okay. So how can we have the configuration manager make better reconfiguration choices? And this is the idea behind our protocol Phoenix, which presents a new approach to reconfiguration called reactive reconfiguration.
It's not even it's a comment. I'm just going to say it because it's really short. I mean, it sounds like you're saying that like the configuration manager is omnipotent, right? It's available and consistent and correct, but it's not omniscient. It can't see replica to replica communication. So you've asked us to swallow this big thing that you said you're going to fix later, and I can't wait, right? Which
Yeah.
is that like this magic configuration manager that's omnipotent. But it's interesting that omnipotence isn't enough.
Yeah.
Right? So that's cool.
Yeah, so the idea behind reactive reconfiguration is using fault detection to drive reconfiguration, right? We have all of these localized fault detection information at the replicas, and we have this essentially blind configuration manager. Why don't we just aggregate the localized fault detection information at the configuration manager and allows it to see what the replicas are seeing to make better reconfiguration choices? So let's consider a system under Phoenix. And suppose one of the replicas here is, again, sending garbage. And then shortly after, we have another replica, R4, crashes. Now, the remaining replicas are insufficient to continue processing requests because we need a quorum of n minus fb to be able to commit values. So the correct replicas, though, had their suspicion about who's faulty because, well, R3 was sending them garbage this whole time. So instead of ignoring it, they can relay this information to everyone and the CM by sending a vote message, including in it who they suspect is faulty and what is the latest consensus decision in their log that reflects their latest state. And as seen before, when the CM collects enough of these vote messages, it can now send a reconfiguration request. When replicas receive this request, they will perform a reconfiguration step where they will reach agreement on this new configuration and also synchronize their logs. After which they can reply to the CM, and then the CM can introduce the new replica. Cool.
May I add something here? So this process seems very much aligned with leader election or view change protocol.
Like view change, yeah.
When people complain, broadcast complaints, and if you receive a quorum of complaints, then that's basically an echo. Then you send a ready, right? And then if you receive f+1 ready, you amplify ready. And you do all that because not only you should change R5, but also you should inform R0, R1, R2 that a new member came in. So you want this eventual delivery. That's why you need another round of messages ready to do that, right?
Yeah, so exactly. The view change happens kind of similar, right? Where a replica that receives f+1 view messages will also broadcast this view change. So a similar process here happens. In the previous slide, when a replica receives f+1 complaints, like vote messages on who is suspected to be faulty, they know that at least one correct replica has suspected this replica to be faulty, so it's safe for them to commit to this as well. This ensures that everybody commits to who's faulty once at least one correct replica suspect that replica is faulty.
Well, that's only one round. The first round gives you consistency, right? So you agree, but it doesn't get you this eventual delivery. You need another round so that everyone receives the same message. You don't want some part of the network to think that this new person went out and someone else came in, but the other part of the network doesn't do anything.
Well, if a replica sends its own vote after receiving f+1, eventually all of the correct replicas will vote for the faulty replica to be removed. Because f+1 triggered their own vote. So eventually if a replica sees that f+1 have voted against another replica, they will also commit to voting against it.
I think his point is what happens then? Like when do you know you can keep going? Like that everyone has seen it?
Everyone eventually has to agree to the members of the
Right.
network, right?
Which is why they have to, like for a view change at least, why they have to commit, right?
Yeah, so in here, when the CM receives enough of these matching votes, that's when we can commit to a new configuration.
Yeah, so the CM, correct me if I'm wrong, I was going to ask this later, but the CM is actually carrying out a two-phase, it's the coordinator of a two-phase commit.
It's the coordinator.
Because it's fundamentally, there's two phases. And in the first phase, it's like, can you all, it's not all, right? It's like, can 2f+1 of you do this?
Mm-hmm.
And if the answer is yes, there needs to be a second phase where it says, this is the new view and
So, sure, so yes. So the first round, again, is about consistency, so that we all agree. Like if two of us add someone to the network or remove someone from the network, we agree on who that is.
Mm-hmm.
But there is another round that's needed to be done so that we make sure that this propagates to everyone in the network.
Yeah.
Once you do two rounds, that's done. And then you mentioned also these CM. Yes, CM can act as some process that collects signatures and sends it to everyone. Like if you have 2F+1, because it's authenticated, it can collect these signatures and send it to others.
And this
But
simplifies
you should-
things because typically that would be the role of a leader, and the leader's reign could end in the middle. Like there could be a view change in the middle. So the fact that it's a CM and there's only ever one CM and it's omnipotent simplifies this.
Yes,
So
but
the-
we
there's-
have to assume, as you mentioned, that CM doesn't crash.
Mhm.
So
Yeah.
in fact, the Braca algorithm that I was talking about 2 phases doesn't use this because it's not dependent on any node to stay off, right? If still you have only F crashes, it can continue to do that.
I think Tuan's saving
Yeah.
something for the end of the
Yeah,
But
I'll
for right now, he is asking us to imagine this fiction.
yeah,
Yes.
I'm asking you
Yes.
to make the same assumption that the previous systems are making, that it's there, it's always there, and it's doing the right thing.
All right.
Yeah,
So we should let you go.
yeah. No, but that's a
We
good.
will talk more.
That's a good point because I mean in the Paxos paper, Lamport did say that to make the CM highly available, you can do replication. You can replicate the CM as well.
Ah, but that's easier said
Paxos
than done.
all the
because
way
then
down.
it's- then it's
You can
all
do
done.
Paxos on the replicas and Paxos on the CM, but
Just real quick clarification, you're talking about vertical Paxos.
vertical
not
Paxos, vertical Paxos. Sorry. Yeah. So for now, I hope that you buy the same assumption that I'm making
Yeah, we could.
about the configuration manager.
Yes.
So I'm doing what the cool kids are doing for now, but I'll do something cooler later. I hope.
Tuan, can I ask something?
Yes.
Just a small clarification. In this slide, when you talk about the the reconfigure kernel in the second box,
Yes.
it's you are running the consensus here, but with this smaller quorum.
Yeah. So
Right or okay.
yeah,
Okay.
but with a
So it's
smaller
normal-
smaller quorum.
Yes.
Mhm.
It's a normal reconfiguration, but what you change is the size of the quorum during the reconfiguration.
Yeah. Yes.
It's small, it's different than the commit quorum.
Yeah. The commit quorum is n minus FB. This is smaller because it could be the case that we have both FB and FC faults.
Right.
So
I know.
we needed a smaller configuration.
Yes. No,
Yes.
otherwise there will be no, it will be blocked.
Yes. No liveness. Yeah.
And I would like to make just a comment about this thing about the configuration manager being always available and so on. For example, in systems like BFT Smart, the main idea was that this would be like a client, a special client, an administrator that sometimes start and change the system. This is different, for example, when we talk about vertical Paxos, where they really require this at runtime in the system. I think in your case, you need probably something that is closer to vertical Paxos because you are really doing something that typical BFT system doesn't do, right?
Yeah.
You don't monitor replicas.
Mm-hmm.
I don't want to go
Anyway.
too far off topic, Allison, but I can't help asking. So in BFT Smart, I mean, what happens if there's more than one of those special clients concurrently running? Is that a safety hazard?
No, because
No, because they are just normal clients.
I see.
They just have to do this.
I got you.
Yeah.
got you,
Yeah.
so
There's no monitoring that's
I was
happening.
imagining like two giving conflicting view changes concurrently if you just do what they say. Anyway, but
yeah.
They still have to do a view change afterwards, so.
Yeah, it's not a problem because what happens here is that you are saying add this guy or remove that guy. What happens in the worst case that if you start removing more than what you should, it stops because it gets stuck because there is
There's no enough.
no help because at some point, yeah.
gotcha. And there's always a view change after, so everybody agree. Yeah, gotcha.
Yeah.
Sorry for getting off topic.
Yes.
No. This is it's interesting discussion. Okay, cool. All right, so being able to detect and replace faulty replicas allows us to deal with this problem of accumulating faults, because we're effectively resetting the accumulated faults that are bounded by our FB and FC thresholds. Right? And this allows the system to tolerate an unbounded number of faults in the long run, so long as they adhere to our fault tolerance bounds. We also have to take into consideration the notion of safety, though, where consensus instances that are decided must not be overwritten, and that the new configuration needs to start where the old configuration left off. So in our system of 5 replicas, consider our system of 5 replicas, a commit quorum of n minus FB prevents consensus decisions from being overwritten. However, during reconfiguration, it is possible that our reconfiguration quorum intersects this commit quorum at only one correct up-to-date replica. And we need a way for this correct up-to-date replica to be able to prove that its consensus decisions are valid. And we can do this using digital signatures and quorum certificates. So what are quorum certificates? Well, quorum certificates are what replicas use to determine when it's okay to move on during consensus. Right? So let's take a look at an example in PBFT. When a client in PBFT receives a reply quorum of F plus 1, it means that F plus 1 of these replicas have a commit certificate, or have received enough commit messages to form a commit certificate. And out of these F plus 1 replicas, at least one of them is non-faulty. And the commit messages in this replica's commit certificate must have come from replicas that have a prepare certificate. And out of these replicas, at least F plus 1 of them are non-faulty and can vouch for the consensus instance containing the client's requests. Okay. There are 2 ways in Phoenix in which we can guarantee that the correct replica that's included in reconfiguration can also attest for its consensus decisions. The first approach is we can keep the reply quorum small at FB plus 1. Again, this ensures that at least FB plus 1 of the replicas have received enough commit messages to form its commit certificate. And out of this FB plus 1, at least one of them is non-faulty. And the commit messages in this non-faulty replica must have come from replicas with a prepare certificate. And we can have messages in this prepare certificate be signed so that during reconfiguration, the correct replica will be able to prove that its consensus decisions are valid. The second approach that we can use is we can have the clients just simply wait for more replies. Right? Here we have the clients wait for n minus FB replies. Again, n minus FB replies means that as many replicas have received enough commit messages to form a commit certificate. And out of these replicas, during reconfiguration, the correct replica will be able to attest for its consensus decisions if we require that the commit messages be signed. Okay, cool. So next, let's discuss the evaluation of Phoenix. In the first evaluation, we wanted to see how adding signatures and varying the reply quorum sizes affect the performance of the system. So for this first evaluation, we performed 2 sets of experiments. the first experiment, we have client requests and replicas replies be empty, so 0 bytes. For the second experiment, we have requests and replies be of size 1K. And for each experiment, we compare the baseline performance with the design where we have a smaller reply quorum but enforce signatures in the prepare phase, and then the design with the larger reply quorum but enforce signatures in the commit phase. So on the right, we see that for the 0-byte benchmark, having a client, having a larger reply quorum causes the client to wait for more replies between requests. Thus, it slowly decreases the throughput and increases the latency. We see that for the 1K benchmark, the throughput drops drastically. This is because of the overhead of message transmission. For both experiments, we see that adding signatures to the prepare phase also impacts performance. This is because we implemented Phoenix on top of BFT Smart. And in BFT Smart, there's this option to do commit signatures speculatively, where a replica that received at least one prepare message can create spawn a thread to create and sign a commit message before it even have a quorum of prepare messages. So this is not possible for the prepare messages themselves because the replica have to wait for the pre-prepare from the leader before it can create its own prepare. So from this experiment, we conclude that using a larger reply quorum in Phoenix is a better approach than a smaller reply quorum, but enforcing prepare signatures.
Can you imagine some scenario where the other approach would be better, or?
Yeah, so that's a good question. Because we did this test in a local cluster, Chameleon Cloud. So all the replicas are within the same server. In a situation where the replicas are distributed widely across the world, for instance, having replicas having clients wait for more replies would have a larger impact on the performance, right? Because now they're having to wait for replies from a longer distance.
Yeah.
So yeah, that's a good question. In this scenario where all the replicas are close together, the larger reply quorum makes sense. Okay, for the next evaluation, we wanted to see how Phoenix recover from faults using reconfiguration. In time period T1, we have clients spin up and they start sending requests to the replicas. So we see the throughput gradually increases. In time period T2, we have the leader halts, which causes a view change, but this view change succeeds because there are still enough replicas left in the system. In time period T4, the new leader crashes, and now there are no longer enough replicas to run consensus. So the system undergoes a reconfiguration step, where the replicas vote out one of the faulty replicas. And this reconfiguration step is successful, and the replicas, there are now enough replicas left in T6 to continue processing requests. Right? So we see the throughput once again stabilizes. Okay, all right, so to sum up this work, we recognize that permission BFT systems prioritizes consistency over availability. And in a deployment where faults can accumulate, availability can be affected once the accumulated faults surpasses a threshold. We recognize that fault detection and reconfiguration exists in these systems, but are not utilized to their full potential. Right? So we present a new approach to reconfiguration called reactive reconfiguration that uses fault detection to drive reconfiguration to allow us to detect and replace faulty replicas and allow the system to survive prolonged deployments.
So Tuan, I just want to
Cool.
make sure that you're aware of the time. We're about 45 minutes into the talk.
Oh, shit. Okay. I'm like halfway done. I got to speak fast.
You got to speed up.
Okay. All right. So,
We'll ask fewer questions.
okay. For the next part of my talk, we'll look into how fault detection can help blockchain systems. So 3 of the main characteristics that differentiate blockchain systems from permission BFT systems are membership, replication, and performance. Unlike permission BFT, where the set of replicas are fixed and every node knows about every other node, blockchains have open membership, where anyone's free to join. There's a much larger set of nodes, and every node only knows about a subset of every other node. Replication is also different. We have seen that permission BFT prioritizes consistency over availability. Blockchains prioritizes availability over consistency. So it is possible that consensus decisions in blockchains can be reverted. And lastly, there's a difference in performance, with blockchains generally having a much lower throughput than permission BFT systems, often in the orders of magnitude. So for my next project, I will talk about detecting eclipse attacks in proof-of-work blockchains. Recall that one of the characteristics that differentiate blockchains from permission BFT is that membership is open and that every node only knows about a subset of every other node. And the way consensus is done is a node mines a block, and then other nodes will acknowledge this block and mine on top of it as it propagates over the network. And due to the open nature of the blockchain and the limited connectivity that a node has, it is possible for an adversary to control all of the connections that a node has with the network. And with a monopoly on these connections, the adversary can launch what's called an eclipse attack, where it can suppress new blocks that are mined by the rest of the network, or generate its own malicious blocks to feed to the victim node. So let's take a closer look at the consensus protocol to see what we can use to help us detect these attacks. Right? So in proof of work, the way consensus is done is that transactions are packed into blocks, similar to how client requests are packed into consensus instances in permission BFT. But unlike permission BFT, the validity of a block is not determined by a quorum, but instead whether or not a node has solved its puzzle. Right? Solving a puzzle means hashing the block's content with random nonces and finding a nonce that meets some difficulty target. There's a notion of expected block time that nodes must produce blocks by. So if a block is produced too quickly, the difficulty increases. And if a block is produced too slowly, the difficulty decreases. And there's also this notion of a minority attacker, where a single entity shouldn't have 51% or more of the network's hash power. OK, so which of those characteristics can we use to help us detect eclipse attacks? Well, we can first rely on the assumption that the attacker will be in a minority. A minority attacker will statistically mine blocks at a slower rate than the majority. And recall in the previous slide that a block that's mined too slowly will cause the subsequent block's difficulty target to decrease. And perhaps we can monitor this difficulty value to help us detect the eclipse attacks. But that's not so straightforward, though, because the blockchain, membership in blockchain is open. So the difficulty value naturally increases and decreases as miners join and leave the network. So we can't use a single difficulty value as a reference point. We need to adjust this value as we go along. But we can't adjust it on a block-by-block basis either, because the notion of average block time means that there's some tolerance to how much difficulty can drop. So an adversary can cause a slow but valid decrease in the block's difficulty until it reaches a point where it's low enough that the attacker can mine blocks quickly. Okay, so we need to monitor this change over a series of blocks. And this is the idea behind our work, which is we present a runtime difficulty monitoring algorithm. And our algorithm groups blocks into fixed size checkpoints. Within each checkpoint, we use the median difficulty value to calculate the reference difficulty value, theta ref. And with theta ref, we calculate theta min, which is the minimum difficulty value that new blocks must meet based on some allowed drop in the difficulty value. And as enough blocks are mined, we shift over the checkpoint and calculate the new reference and minimum difficulty values. All right, so how effective is our monitor? Well, in our first evaluation, we wanted to look into the possibility of false negatives. Right? So false negatives are non-detection by our monitor when the node is actually under an eclipse attack. So we looked into various values of theta min, and for each value, we looked into the ideal checkpoint sizes that's needed to prevent the attacker from evading our difficulty monitor. And for various values of theta min and checkpoint sizes we evaluated, the possibility of an attacker evading our detection is extremely low. Next, we look into the notion of false positives. So false positives are blocks that triggered our algorithm when the node is not under an eclipse attack. To evaluate this, we ran our monitor algorithm against all of the historical blocks in the Ethereum blockchain. Historical blocks are all but just the most recent 96 blocks, so the majority of the blocks in the blockchain. It turns out that a number of blocks did trigger false detection in our algorithm. But upon closer inspection, all of these false positives came from the result of hard forks or software upgrades due to API updates or bug fixes. So during these major events, it expected that a node be shut down and upgraded software to be accepted by the rest of the network. So these false detections are not of our concern. All right, so to summarize this work, we recognize that, again, blockchains prioritizes availability over consistency. And an adversary can leverage the limited connection that a node has and the probabilistic finality of blocks to launch a major consistency attack called the eclipse attack. And our solution to detecting these types of attack follows the theme of this thesis, which is leveraging fault detection mechanisms that already exist within these protocols to detect this attack. Right? And our solution relies on the difficulty values of the blocks to detect the attack. Our work that was presented at ICBC actually considered it a slightly harder problem, where we needed to detect eclipse attacks in blockchain applications that ran inside secure enclaves on untrusted hosts. So in this setting, an adversary does not even need to control all of the connections that a node has, right? It just needs to control the host on which the application is running. But even in this scenario, our difficulty monitoring algorithm works just as fine. All right. just a few more slides left. All right, so far in our fault detection journey, we first looked at permission BFT systems, how they prioritize consistency over availability, and how accumulating faults can affect availability in prolonged deployments. And we presented a protocol that helps with that. And then in blockchain systems, we looked into how they prioritize availability over consistency, and that an adversary can leverage the limited connections that a node has and the probabilistic finality of consensus to launch an eclipse attack. And we presented a solution for that. Are there other ways in which inconsistencies can happen? Yes, there are. And it has to do with the fact that blockchains are slow. So, blockchain practitioners have recognized that low throughput is a critical issue in blockchains, right? Throughput is low because each block has limited space and can only be produced at certain intervals. So, the majority of the scaling solutions that exist today rely on off-chain scaling, where transactions are done off-chain and occasionally an update is pushed on-chain. Of these scaling solutions, state channels is one of the leading approaches to off-chain scaling. In state channels, two parties can encode the off-chain state on a smart contract. And then state updates are done through direct communication. At any point in time, either party can send a transaction to the contract to synchronize the on-chain state with the off-chain state. And an execution fork can happen when a malicious party updates the on-chain state with a stale off-chain state that benefits them. And then closing the channel before the honest party can even update the contract. So in our work that was presented at ICBC of 2022, we recognized this execution fork is a major problem, and we present a solution to detect these attacks by encoding a fault detection mechanism inside the state channel contract itself. Cool. So smart contracts are pretty cool. In fact, they're the backbones of all major layer 2 scaling solutions that exist today. But what are they? Right? They are these trustless self-executing code that exists as part of the blockchain data itself. And because of that, they inherit the high availability guarantee provided by the blockchain. And it's trustless because the code is public and anyone can verify its state transitions.
Sorry, is that the definition of trustless? What is the definition of trustless?
Trustless is, in this context, it's the code is public and then anyone can verify its state transitions.
The idea being no trust required.
No trust required.
Gotcha.
Like it's an integrity property of the code.
Gotcha. Thanks.
Okay, so recent works have shown that these smart contracts can be adapted to manage membership for an application on-chain. Right? The way it works is the contract will encode the set of members on-chain, and then the application can run with these members off-chain. However, these membership management mechanisms that are in these works lacks a way for the smart contracts to detect any faulty members on-chain. So is there an avenue for fault detection here? Yes, there is. And that brings me to...
I think it's going to be no this time.
I think you know where I'm going. But yes, so that brings me to my final work, which is automating fault detection using smart contracts. And this work was recently accepted into DSN. And in this work, we propose a set of smart contracts to manage membership on-chain. And it has the capability of authenticating off-chain components using digital signatures. And this opens up three ways in which we can do fault detection. The first is we can detect equivocation, right? So suppose the off-chain members are communicating, and then one of the replicas, R0, is sending conflicting messages to R1 and R2. When R1 finds out about what R0 says to R2, it determines that it conflicts with what it received from R0 itself. So with these signed messages from R0, R1 can send them to the smart contract, which will validate them and then remove R0 from the replica group. The second way that we can do fault detection here is whether or not replicas' credentials have been leaked. Right? So replicas communicate using their private keys. So suppose R0's key has been leaked, and R1 finds out about it. It can send a message to the smart contract with a message like, hey, my key has been leaked, and sign it with R0's key. And the smart contract can validate this message and remove R0 because communication with it can't be trusted anymore. And then lastly, we can encode a voting mechanism. Right? So replicas can vote on who they suspect is faulty and then remove the faulty member once enough votes have been received. Wait a minute. Voting, removing nodes. It sounds a little bit familiar. So let me bring you back to like 30 minutes ago. Remember one of the assumptions we made about Phoenix? That there's a configuration manager, it's trusted, but it's cool because everyone's doing it, so we'll do it too. But what if we can remove that trust assumption, right? In our work in the Centigram, we propose a contract that can authenticate components off-chain using digital signatures. So with this, we can encode the configuration manager as a smart contract, right? So let's revisit the functionalities of the CM, right? All it does is it collects these votes, it validates the signatures and the content, and then once enough votes have been received, it just removes the faulty replica, right? So the way we can encode this to remove trust in the CM is pretty straightforward. We encode the members in the smart contract, along with a voting and authentication mechanism. And then when the replicas send their votes to the CM, it validates these messages. And then when enough votes have been received, it can then just remove the replica from the replica set. Right. So this not only solves the problem of trust in the CM, it also solves the problem of everyone must learn of any reconfiguration changes. So in BFT, not only replicas, but clients must know of any configuration changes, right? Because they need to know who to send their requests to. So in here, both clients and replicas can simply just monitor any state changes in the smart contract to determine any new configuration has happened. Okay, so our work that will be presented at DSN actually uses this to build a much cooler system. We use it to build a highly available publish subscribe system. And our smart contracts are not only able to authenticate components using digital signatures, we are able to authenticate secure enclave components on-chain. And with this, we're able to leverage both the confidentiality and integrity guarantees of the secure enclave, but also the high availability guarantee of blockchains. That allows us to have highly available and confidential publications. In addition to being the first system that is able to authenticate secure enclave on-chain, we're also the first system to support on-chain notification. So that's pretty cool, but the work is not public yet, so for audience members who are interested, I can send you a copy of the paper. All right, so we're well over time, I'm sorry. In our fault detection journey, So we've finally reached the end of our fault detection journey. To sum up my thesis work, I looked into the fundamental trade-offs that permission and permissionless BFT systems make, how they affect the availability and consistency guarantees, and how we can use fault detection to help make these systems more robust. And yeah, so my work is in chronological order. If you have a time machine, this is because one of my, the work in Phoenix got rejected many times before it got accepted. So that is the end of my talk. Thank you.
Questions from the audience?
I have one small question. So the problem, the PBFT client problem, what is this just another thing that's solved by the clients are supposed to broadcast their requests to everyone, or?
The clients finding out about the new
Yeah,
configuration.
like when new configurations happen.
Yeah, it's not discussed in PBFT, but in BFT Smart, I remember in the repository there's a line that says, we need to take care of the problem of distributing the new configuration to the replicas and the clients. So it's a small problem, but it is a problem that clients need to learn of the new configurations. Presumably, you know, if there's a trusted configuration manager, when after reconfiguration, it will take care of the distribution itself. So that's one way you could do it. Yes.
Yeah, may I know the protocol again, the one where you had these DM, but you didn't have smart contracts for it. How does the configuration work there? The one that you were talking about?
The Phoenix without blockchain?
Yeah, Phoenix without
Phoenix,
blockchain.
right,
Yeah, let me
without
go
blockchain.
back.
So F+1 complain and the DM collects those, and then what does it do with that?
No, so F+1 complains, but the CM waits for N minus FB matching complaints. Sorry, if you, right.
Okay.
So N minus FB matching complaints means that enough correct replicas have reached agreement in removing the faulty replica. So it's not just F+1. It's waiting for potentially all but the faulty replicas to commit to the view change. Or the reconfiguration.
And it's a smaller quorum that's kind of the key there, right? Because it's a smaller quorum than the commit quorum.
Yeah.
Well, N minus FB is pretty large, no?
No, the commit quorum, we cannot commit values anymore after the second box here because we can't have N minus FB. But we can have a vote quorum of N minus FB minus FC.
Minus FC. Okay.
Minus FC.
And then what does CM do there after receiving these many signatures?
So it will construct a new configuration that replaces the faulty replica with a new one. And then it will send that configuration to the set of replicas who will run consensus to reach agreement on this configuration.
It's essentially a view change that's happening there, right?
Yeah, but with a smaller...
But you can do it with a
smaller
voting
quorum.
quorum for the view change because you were stuck because
Yeah.
you were wrong about F, right? I mean, this is the thing that, like, you know.
Forgot about Dre.
So it's a smaller quorum, that's why it works in this case. And then the next slide shows why we can have a small quorum and then not cause everything to go to shit. I hope that answers your question.
Okay.
I have a question. I have several, but I can start with one. Why do we need this FC? I mean, you can use the same idea of the system, the feature you are including in the system, but I can't see why you need this specific crash fault. I mean, you could have, you could remove some replicas as long as you still have enough how can I say, enough replicas to make a quorum. For example, you never have two faults if you tolerate just one. This is the common practice. For example, when people deploy Zookeeper, they typically deploy f equals 2 because they want to be able to still tolerate a failure
Have a
while
safety
they are
margin.
still
Yeah.
removing one.
Yeah, so earlier in the slide, yeah. So earlier in the slide, I talked about how accounting for this in a BFT system would be too expensive, right? So if we were to consider one crash and one Byzantine fault, that would have our system be of 7 total replicas in the typical BFT.
I think it's not correct. I think it's 3FB plus 2FC plus 1. I think.
The
So there are Byzantine works that consider crash faults separately, and there are different thresholds for them, you know?
yeah, so
It's not 3FC plus 1, really.
yeah, so I think there was a recent work that shows
Yes.
that we can reduce it to 3FB plus 2FC
Yes,
plus 1.
stuff like that, yes.
But I leave it at this just to simplify things, because earlier I said 3F plus 1. Here I say 3FB plus 3FC plus 1. But even with 2FC, our system under Phoenix considers an even smaller deployment, right? 3FB plus FC plus 1. And it's not that we are able to always commit values with this number of faults with this deployment. We're saying that when we have this number of faults, we're able to get out of it and reconfigure to have enough replicas again.
I think I get it. I get it now. I mean, yeah. In fact, what you are doing is with a configuration manager and the Phoenix model, you can tolerate crashes plus the standard Byzantine faults, but you can tolerate crashes in a less resourceful way, spending less resources.
Yes. Yes.
Because you have someone to help you reconfigure.
Yes.
Yeah, exactly.
So the idea behind Phoenix is we can survive the same number of faults with smaller number of replicas, and we're able to detect the Byzantine faulty replicas that would have otherwise stayed in the system, right, under the normal BFT assumptions.
I get it. Another thing that I would like to ask is that have you considered not? I know in the end you solved the problem putting it in the blockchain, and I think it's very cool. I remember your qualification. We talked a bit about that. I think I mentioned this could be an interesting. I think it works pretty well. I never thought about this after we talked in your this proposal or qualification, but it works quite well. I have to confess that I don't like much the public subscriber, but I think the way it's organized in your thesis probably is the part that I less like your thesis. But anyway, I could understand the idea and it makes sense. But the way you presented with now we have the configuration manager in the blockchains. It's really.
Yeah, so I wanted to showcase the bigger system that we built using it, but you're right. Yeah, it doesn't.
I think he's praising how you presented it in the talk.
Oh,
And I
Yes,
agree.
yes.
oh, thank you.
I'm praising the talk and saying that the thesis is not so good. The subpart.
Yeah, it's an underhanded compliment.
Oh, sorry. Thank you.
No, but anyway, my question is about, have you considered using the configuration manager replicated together with the replicas?
With
I mean, imagine that each replica, you have also one replica. I mean, the configuration manager itself will be replicated using state machine replication.
Yeah, that's a good point, because I do think it's possible, right? Because if we consider a system under Phoenix, and we also have the replicas run some sort of like reconfiguration protocol inside them, we can just have this protocol run with a smaller quorum, and it will still work. I think so.
Will it?
What is the, like, is vertical Paxos the one that's Paxos all the way down?
Yeah.
So how do they express the bound in that? Like because there's got to be some assumption that it's like this many crashes and
I don't remember.
because it seems like there's like maybe some discrete limit or something that's happening.
So, like, I'm not sure if, I mean, it's definitely interesting food for thought. I'm not sure if it'll work. I mean, if you know, if you bootstrap in that way, won't you need a 2F+1 quorum to do the thing? Like the unique trick that you have is when you got F wrong and there was exactly one more crash than you budgeted for,
Mm-hmm.
you can like reverse time and you can unstick yourself, right?
Mm-hmm.
It's not clear to me if we're using the consensus mechanism to effectuate the reconfiguration, how you do that trick with a smaller quorum.
So I'd probably have to think a little bit more about how we would integrate the configuration manager at the replica itself.
I'm asking that because in BFT Smart, we have this extension for trying to make BFT Smart a blockchain. 2020, we published in DSN.
Mm-hmm.
And one of the things we changed is remove this administrator, trusted administrator,
Gotcha.
and make the replicas itself reconfigure the system. So basically, the idea is that when F+1 replicas want to reconfigure,
Mm-hmm.
then the system reconfigures. It's the same thing, but imagine that you have, instead of having one configuration manager, you have the replicas itself act as clients
Yeah.
issuing reconfiguration requests.
Uh-huh.
And then when you have enough of them, you do. I don't know, what complicates in your case is the fact you are using a different form.
Right.
Yeah.
Well, and the other thing, I mean, one of the reasons that we needed the number that we did was actually a sync consistency issue.
Yeah.
Too, right? Like that we wouldn't lose state in certain.
Yeah, we wanted to be able to ensure that consensus decisions don't get lost when reconfiguring. But yeah, that's an interesting thought, Allison.
Yeah, maybe we should go back to that paper and look at.
Yeah, I'll have to go back and look at your paper. That's
I
interesting.
think someone mentioned vertical part. Too small. The room is appearing to me too small. But anyway, my visualization here was. But anyway, I think in vertical parts, the way they do that, if I remember correctly, is for the vertical parts itself, it's just F+1 replicas, and for the configuration manager, you use standard parts.
Mm.
Because otherwise, it will be the configuration manager requires another configuration manager.
Yeah.
Right.
But so
Recursive problem.
so then you have two upper fault bounds to consider
Yes.
then, right? Yeah.
Yes.
Mm.
And they assume it's in different.
They're independent.
Sets of-
Or,
Yeah. there's
Yeah.
no independent.
Let me see if I have
Should
any
we,
other. I think most of my other comments were clarified in the presentation or.
Do you want to move to the second phase here, Peter?
Yeah, I think it's time.
Yeah. All right.
Oh.
I think that means we're kicking you out. Yeah.
Oh,
And we'll stop the video too.
Yeah, I think my other comments are about the text, not really.